In the following lecture, we're going to try and compare acid strengths of different organic compounds that can behave as acids. So the first thing is we need to define what acids are. Acids are proton donors or any molecule that produces H plus 1 ions. So as an example, we have a molecule that is HA, and if it releases or produces H plus 1 ion, so it's going to be termed or classified as an acid. So lots of organic molecules can behave as acids. They are capable of releasing or producing H plus 1 ions. So the compounds that we are going to discuss when we are comparing the acid strength, those compounds are: the first one is alcohols. We're going to discuss the strength and comparison of alcohols behaving as acids. We're going to compare phenols as well. Phenols are also acidic. They're capable of releasing H plus 1 ions. And the same is true for carboxylic acids. They're also capable of releasing H plus 1 ions. So all these three molecules, they are acids. They have acidic behavior and they release H plus 1 ions. And the general trend is that alcohols are considered to be the weakest of the acids. They're very weak. They have less dissociation, even less dissociation compared to water molecules. So they don't produce a lot of H plus ions. And as phenols are somewhere in the middle, whereas carboxylic acids are considered to be the strongest organic acids. They release H plus ions as well. In total, all of these three compounds, all organic acids, are considered weak acids. So we are just comparing them. So in comparison, all of them are weak acids, but in comparison, carboxylic acids are considered to be the strongest between the three, and alcohols are considered to be the weakest between the three. Now, here's a table that's going to summarize the reactions. Acids usually react with metals, bases, and carbonates. Carbonates are also weak bases. So they react with hydroxides, with carbonates, and with metals. Now, alcohols are considered to be the weakest. So alcohols only react with very reactive sodium metal. So only react with sodium metal. They don't have any reaction with NaOH, which is a base, and they don't react with carbonates as well. So they're not very good acids. They are very, very weak acids. Phenols, on the other hand, are slightly stronger. So they react with sodium. They also react with sodium hydroxide. So they react with bases as well, but not with carbonates, which are considered to be weak bases. Carboxylic acids, on the other hand, they react with all three of the compounds. They react with metals, they react with metal hydroxides, they react with metal carbonates as well. So carboxylic acids, in relative comparison, are the strongest of the acids, of the strongest of the organic acids. Now we're going to start a comparison with alcohols. Alcohols are the weakest of the acids, and they dissociate even less compared to water. So here's an alcohol. All alcohols have this OH group in them. And remember, when an alcohol produces H plus 1 ions, it's always this OH group that releases H plus 1 ions. Not any of the hydrogens would be lost, but the OH hydrogen would be lost. So it very weakly ionizes, ends up producing H plus 1 ion, and this ion, negative ion over here, which is going to be called, it will be called ethoxide ion. If it's ethanol, then it's going to produce ethoxide ion. So you can figure out the naming yourself: propanol, propoxide ion, methanol, methoxide ion. So this is the ion that is going to be produced. This oxygen is going to have a negative charge. The H plus 1 would be released. But this reaction does not happen very frequently because it's very less dissociation. So if you have thousands of ethanol molecules, only very, very few percentage, a very small, tiny percentage is going to dissociate, and it's going to produce these ions. Now, since alcohols are very weak acids, alcohols only react with highly reactive group 1 metals, and even then the reaction is extremely slow. Now, whenever a metal reacts with an acid, it produces salt plus hydrogen, and alcohols are going to do exactly the same when they react. So here you can see sodium metal reacting with a methanol molecule. What would happen is the alcohol, the H, the acid H. Remember, none of the other hydrogens are going to be displaced. Sodium is going to come in and it's going to knock out this hydrogen. It's going to take its place. What's going to be produced is that it's going to be CH3O minus 1. The H is going to be knocked out and Na plus 1 is going to take its place, and hydrogen gas would be produced as a result. And to balance this equation, there should be half molecules of H2 gas that are going to be produced. So this is the reaction that would be taking place. Just like any salt formation, all salts are produced in exactly the same way, that the H in the acid, so not the other hydrogens, not the carbon chain hydrogen, the OH hydrogen is going to be displaced. Sodium is going to come in, it's going to knock it out, and it's going to produce, the H is going to be lost, it's going to be producing hydrogen gas, and this salt would be produced, and the name of this salt is going to be sodium methoxide. Remember our naming. This was ethanol produces ethoxide, methanol produces methoxide ion. So this negative ion would be called methoxide. So the name of the salt is going to be sodium methoxide. So this is the only reaction that alcohols undergo, and it's going to be a very slow reaction. So a very slight effervescence would be seen. You're going to see bubbles of H2 gas that would be produced, but there would be very slight bubbles. Not a lot of bubbles are going to be produced. Very slow reaction. Now let's try and answer why are alcohols considered to be weak acids and why are they weakest compared to all the others. Now I've written down the reaction of an alcohol, ethanol in this case, dissociating, the OH breaks away and H plus 1 and this negative ion is produced. Now the reason why alcohols are weak acid is because the reaction is not going in the forward direction. Instead, the reaction is favoring the reverse reaction. So dissociation is not being favored. And this is the reason why dissociation is not happening because of this negative ion. This negative ion has this negative charge. So we're going to focus on this negative charge over here. The problem with this ion is that the negative charge density is very high. So as soon as the H plus 1 breaks away, the H plus 1 is going to be strongly attracted to this negative charge because this is a very concentrated negative charge. And the reverse reaction would be favored. So so the reverse reaction would favor the H plus 1 if it gets dissociated, if it ionizes. The negative charge, the strong negative charge over here is going to pull the H plus 1 back again. It won't let it go away. So it's going to pull the H plus 1 back again and the alcohol is going to reform. So less dissociation would happen. So why is the negative charge density higher over here? The reason rests with this carbon chain, this alkyl chain. Alkyl chains have electron donating effect. Whenever there is an alkyl chain attached to a group, the alkyl chain pushes electrons. It's going to push electrons towards this oxygen atom. And the negative charge over here is going to become more concentrated. The charge density over here is going to become higher. So the main reason, the sole reason why the negative charge over here is higher is because the carbon chain or the alkyl chain has an electron donating effect. And it's going to push its own electrons and which would increase the concentration of charge over here, which is why the H plus 1 would be strongly pulled back. It's going to be strongly attracted and the reverse reaction would be favored and the alcohol would not be able to dissociate or ionize. So what you're going to write is the explanation, the correct explanation for this is going to be, so here's the complete explanation that what you're going to write is that the alkyl chain in alcohols have an electron donating effect. So the alkyl chain is pushing electrons, which increases the negative charge density on the CH3CH2O minus 1 ion. So the negative charge density over here increases, making it unstable. So it's going to have a very strong attraction for H plus 1, which would lead to less dissociation. So as soon as the H plus 1 breaks away, it's going to strongly attract that H plus 1 back again. So less dissociation would happen because of the strong negative charge over here. Another extra point about this is that the longer the alkyl chains, the more would be the electron donating effect, which would make the alcohol even weaker. It's going to make it even a weaker acid. There would be weaker dissociation. So for example, I have these two alcohols. CH3 would have less electron donating effect. If there's a bigger carbon chain, the electron donating effect would be even greater. So in the case of this ethanol molecule or this ethoxide ion, the negative charge over here would be even greater and there would be even stronger attraction for H plus 1. So bigger the alkyl chains, weaker would be the dissociation. So ethanol is going to be a weaker acid compared to methanol. If you have propanol, that would have an even bigger alkyl chain. So the electron donating effect is going to be even greater and the negative charge density over here would be even bigger. So H plus 1 attraction would be even stronger, so even less dissociation. So as the length of the carbon chain, length of the alkyl chain increases, the dissociation becomes weaker and weaker. The second type of organic compounds that can be classified as acids are phenols. So we're going to discuss phenols, which are an intermediate compounds that behave acid behavior. So alcohols were the weakest. Carboxylic acids were the strongest among all these acids in comparison. Phenols are somewhere in between. Now we're going to quickly discuss dissociation of phenols to produce H plus 1 ions. How do they produce H plus 1 ions so that they can be classified as acids? So this is your typical phenol structure. It's a benzene molecule. And I'm going to just briefly, very quickly discuss the structure of benzene in a short while. It's a benzene molecule that has an OH group. It's different from alcohols. Its properties are different from alcohol. So it's not an alcohol. It's called phenols. And it has this OH group. And remember, this is the hydrogen that is going to dissociate when a phenol dissociates. So this H over here is going to break off. You're going to get O minus 1 would be left. H would leave its electrons, and H plus 1 would break away. So this is the dissociation that would happen. It's always the OH that is attached to benzene. Its hydrogen is the one, not any other hydrogen in the benzene. Only this hydrogen is going to break away, and the H plus 1 ion is going to be produced when a phenol dissociates, and this ion would be called a phenoxide ion. So this over here is your phenol, and it ends up producing a phenoxide ion. Now remember this, when we were discussing the reactions, phenols were slightly more acidic compared to alcohol. So phenols not only react with group 1 metals, but they also react with hydroxides and oxides bases. They're going to react with it. They're not going to react with carbonates, which are weak bases. So the strength, because they are stronger than alcohols but weaker still compared to carboxylic acids, they're going to have two of the acid reactions, but not the third one. They're not going to react with carbonates. So I'm going to write down how they're going to react. So here I've drawn a phenol molecule, and I'm going to react it with sodium. So it's going to produce salt plus hydrogen. The salt that would be produced is going to be produced in exactly the same way that the H. This was the acid H. This was the H that would be replaced, and sodium is going to come in, and it's going to replace that H over here. It's going to displace that H, and a salt is going to be produced. So here I've displaced the H. The oxygen is going to get a minus charge, and Na plus 1 is going to displace it. So this would be sodium. It's going to be called sodium phenoxide. That is going to be produced, and it's going to be half molecule of H2 because only one H got substituted. So this would be the reaction of a phenol reacting with a metal to produce salt plus hydrogen gas. So it's a typical metal plus acid reaction. Another reaction that is going to happen that would be very similar is going to be a reaction with NaOH. So here I'm going to write down a different reaction, a phenol reacting with NaOH, a base. It's going to be pretty much the same. The sodium metal is going to go and displace, and the same salt is going to be produced. Plus, a water molecule gets produced in this reaction because base plus acid produces salt and a water molecule. So here's your reaction with a metal, and here's your reaction with a base. What you just need to remember is how to produce the salt. The phenol, the OH, the H is going to be released, and Na plus 1 is going to take its place to produce this ionic compound in both cases. So every time the salt would be the same, except metal with metal, hydrogen gas would be produced, and with a base, a water molecule is going to be produced. Now I'm also going to describe the structure of phenol in a little bit more detail because we need to figure out why phenols are better acids compared to alcohols. So phenol is a typical benzene structure, so let's draw that first. Now here I've drawn your typical benzene structure. This side, focus on these carbon atoms. Now in benzene what happens is that the carbon atom is bonded, is making 3 bonds. Each carbon atom is making 3 bonds. So if you focus on each of the carbon atoms, they're all making 3 bonds. The only difference is, now the issue is that carbon has a 4th electron as well, and each carbon atom has a spare 4th electron. Carbon has 4 electrons in its outer shell. 3 are getting bonded. The 4th electron, so this here is the 4th electron, the 4th unused electron. And so there's one orbital in carbon that is not bonding. It has an electron, but it's not bonding. And they start overlapping with each other. So they start to overlap with each other, and they start forming pi electron clouds. So each one, all of them basically are in parallel to each other, and they would start overlapping with each other. So now you could see that all the 4th unused electrons, they've overlapped with each other, and this is your delocalized pi electron cloud. So there's a delocalized pi electron cloud. So here's your skeletal formula for benzene. This ring basically denotes this. There's a pi electron cloud in each one, on each one of the carbon atoms, and there's a delocalized pi electron cloud. So this ring over here represents that. And also remember that in the skeletal formula, the hydrogens are not drawn. So each carbon atom is bonded with one hydrogen. So you can see one hydrogen coming out of each carbon atom. On one side, there's an OH group. Another thing that needs to be noted about this pi electron cloud is that it has lesser charge density. The electrons are very, very distributed. The reason they're very distributed is that, for example, if you focus on this electron in this unused p orbital. This electron is getting dragged to this side. It's forming a pi electron cloud over here with the neighboring orbital. It's also being dragged on to the right side, and it's forming a pi electron cloud with this carbon's unused p orbital. So the electrons are more distributed. Instead of being focused at one point, the electrons get spread out and they get more distributed, which is why the charge density in benzene is lesser. Now, because of the lesser electron density, remember oxygen has these lone pairs. It has two lone pairs. These lone pairs, their electrons are very concentrated. But if they find a region where the electron density is lesser, the electrons would get repelled from this side and they would actually mix with the benzene's pi electron cloud and they'll get more spread out. So the electrons on oxygen, they're going to start overlapping with benzene's pi electron cloud and they're going to mix with it. Over here, the electrons are very, very concentrated, so they would have a tendency. So benzene overall has an electron withdrawing effect. The electrons actually of oxygen, the lone pairs on oxygen, they get dragged or get attracted to the benzene electron cloud because of the lower charge density, and instead of being concentrated over here, they become spread out on the benzene. So this is one thing that is very important that you should know. So now we're going to discuss why this thing, that the lone pairs on oxygen or the electrons that are concentrated on oxygen, they get dragged and they start mixing with the benzene. How would that affect the pH or the strength of the acids, of phenols as acids? So over here you can see the dissociation of phenol. OH breaks down. Oxygen has a negative charge and the H plus 1 has broken off. Now what I just told you right now, oxygen had other lone pairs as well. I told you that the electron density over here, electrons are very spread out, so the charge density is lesser. Over here, the negative charge density would be much higher because you have lots of lone pairs all concentrated in this tiny area over here. So electrons from oxygen are going to be pulled towards benzene, and they're going to be dragged towards benzene, and they're going to start overlapping with benzene's electron cloud. When they start overlapping with benzene's electron cloud, what happens to the negative charge over here? The negative charge over here decreases or becomes less concentrated because the electrons have gotten dragged away towards benzene and they've started overlapping, so they've gotten spread out. So the negative charge would not be concentrated at this particular point. So over here, the negative charge density is lesser. As lone pairs on oxygen, they start overlapping with pi electron cloud. So all the electrons get dragged or get pulled over towards benzene. So if the negative charge is not very strong, it's not going to attract H plus 1 ions that strongly. So the H positive ions are not going to be pulled or attracted very strongly. So if they're not going to be attracted to this negative charge very strongly, so there would be more chances of the H breaking off. The reverse reaction would not be happening as frequently as in alcohols. Remember, in alcohols, the negative charge was much stronger, so if the H plus 1 broke away, it would immediately get attracted back and it would become undissociated. But over here, dissociation would happen much more frequently because if the H plus 1 breaks off, the negative charge over here would get spread out and the negative charge would not be concentrated at this point. So the H plus 1 attraction would be lesser and that would lead to more dissociation. So this ion, because of the lesser, weaker negative charge, weaker negative charge would not be attracting the H plus 1 as strongly. So the more dissociation or more likely for dissociation to happen and that would decrease the chance of the reverse reaction happening. So what you're going to write as an answer, if they're going to ask you why phenols are considered to be stronger acids compared to alcohols. So this should be your statement that lone pair on oxygen C6H5O minus 1 ion or the phenoxide ion over here overlaps with benzene's pi electron cloud, making phenoxide ion stable, and there's going to be less negative charge density and less attraction for H positive ions. Now another very important thing is that there would be a lot of variation in phenols as well. So if you have an electron withdrawing group that has been attached to phenol, it's going to increase the acid strength of phenol. So withdrawing groups are going to increase the acidity of phenols. So here are some examples of electron withdrawing groups like NO2, carboxylic group, aldehyde or ketones. Now here was what was happening. I told you that phenols, when they dissociate, the H plus 1 breaks off. The negative charge over here overlaps with benzene's pi electron cloud, mixes the electrons, they get dragged or pulled towards benzene. So the negative charge decreases in strength and it no longer attracts H plus 1 strongly, which is why if H plus 1 breaks off, there are more chances of it dissociating and it remains dissociated. So what happens if you have an electron withdrawing group like NO2? Now, NO2 has an electron withdrawing effect. So, NO2 would be pulling electrons towards itself. So, the effect would reach this oxygen as well. More electrons would be pulled by oxygen. So, you can see over here if NO2 is pulling electrons, the electrons which were concentrated, the negative charge which was concentrated over here, would get more pulled towards NO2. So, if it gets more dragged towards NO2, the negative charge density over here would decrease. And when the negative charge density decreases, it leads to even less attraction for H plus 1. So if H plus 1 breaks off, then there are more chances of it remaining broken off. So more dissociation would happen. The reverse reaction would probably not happen as much. The H plus 1 would not be attracted very strongly to this oxygen negative charge because all the negative charge is now spread out. NO2 is pulling those electrons to the other side. Benzene itself was pulling the electrons, and the lone pairs were overlapping already with benzene. But now the presence of this electron withdrawing group is going to pull the electrons even further, and less negative charge over here, less attraction for H plus 1, so more chances of it dissociating. Now, the exact opposite would happen with electron donating groups. So, if you have electron donating groups are going to they're going to decrease the acid strength of phenols. And some electron donating groups are alkyl chains, so carbon chains, if they are present. They have an electron donating effect. NH2, that is also an electron donating effect, produces an electron donating effect. So these groups, if they are present, they're going to decrease the acid strength of phenols. And the reason why that would happen is going to be the exact opposite. So again, repeating, the reason phenols were better acids compared to alcohols, the lone pairs overlaps with benzene's electron cloud, so the negative charge is lesser, and it doesn't really attract the dissociated H plus 1 ion that has broken off. So more chances of dissociation happening. But what if you have a carbon chain? Or let's say you have an NH2 group. Now, NH2 groups themselves have electron donating effect because they have these lone pairs and their lone pairs overlap. So the net effect is that they're donating electrons. So if they're donating electrons, all the electrons are going to be pushed. The effect that would happen over here on the other oxygen is that all the electrons over here, lone pairs, nitrogen's lone pairs are overlapping with benzene's electron cloud. So all the electrons are going to get pushed to the right, and that would lead to an increase in negative charge density. So if there is an increase in negative charge density, the H plus 1 ion is going to be more strongly pulled or attracted by the negative charge. And less dissociation would happen. The H plus 1, if it breaks off, the negative charge is going to be stronger. It's going to quickly attract the H plus 1 and it's going to bond with it. And the phenol would be reformed, so less dissociation would happen. So you don't want that to happen. So the acid strength is going to decrease. There would be lesser chances of this H plus 1 breaking away. So it's not going to produce this H plus 1 ions very easily if you have electron donating groups attached to phenols. Now, finally, at the very end, we're going to discuss carboxylic acids and why they are relatively considered to be the strongest of all the organic acids. So alcohols, hardly acidic. They don't dissociate. They even dissociate less compared to water. Phenols, slightly more acidic. Carboxylic acids, acetyl bond O and OH, they consider to be the strongest of the organic acids among the three. So we're going to discuss why that is the case. So we're going to first discuss the dissociation of our COH or carboxylic acid group to produce the H plus 1 ions. Now this is what a typical carboxylic acid group is going to look like, the displayed formula. It's going to have a acetyl bond O and an OH group attached to it. Remember, it's always the H from the OH. None of the other H is going to break off. It's the H in the OH in carboxylic acid. That is the one that's going to break off and dissociate and ionize. So here you can see the carboxylate ion that would be produced. The OH is going to break off. The H plus 1 ion is going to be produced. So it would be classified as an acid. And the oxygen, on the other hand, is going to have a negative charge. It would have excess electrons. The H would leave those electrons and would heterolytically break off. And also refer to the naming that if you have a carboxylic acid, a carboxylate ion is going to be produced. For example, if you have, so here's an ethanoic acid molecule, 2 carbon atoms. If you have an ethanoic acid molecule, this is the carboxylate group. The H plus 1 from the OH is going to break off and it would ionize. So if this is ethanoic acid, then the ion that would be produced would be called ethanoate ion. So remember the naming. If it was methanoic acid, then the ion that would be produced would be methanoate ion, and so on. Now the main question is, what we are looking for is, Why is this going to be relatively strong acids compared to phenols and alcohols? What's so special about this ion that makes it a strong acid? It dissociates or ionizes more compared to the others. So we are going to focus on this carboxylate ion and how strongly it's going to be attracting H plus 1. If the attraction for H plus 1 is strong, then the reverse reaction would occur and dissociation would not happen, because if the negative charge is very strong, the H plus 1 would be strongly attracted back and it would not dissociate. If the negative charge is weaker, then it's not going to attract the H plus 1 ion, and there would be less chances of this reverse reaction happening. That is not going to happen. So more dissociation could happen, because once this H plus 1 breaks off, the negative charge would not be attracting the H plus 1. So let's figure out what is the scenario, whether the negative charge density over here is greater or whether it's lesser. So I've redrawn this over here, and I'm going to highlight the relationship, whether this oxygen negative is going to attract H plus 1 or not. One thing that you should notice is that there's a C double bond O group in the carboxylate ion. What this group is going to do is, because oxygen is very electronegative, so this highly electronegative oxygen is going to pull electrons towards itself. So electrons, the negative charge density is going to be attracted by this oxygen towards itself. So what would eventually happen is that this negative charge is no longer going to be distributed or concentrated at this particular oxygen. The other oxygen is going to pull those electrons, and it's going to pull them and bring them closer to it. So all the negative charge that was concentrated over here is going to drift, and it would eventually, what would happen is that the negative charge would be distributed between the two oxygen atoms. So the negative charge is no longer going to be concentrated at this part, at this particular part, which is going to decrease the charge density. So the negative charge density over here is going to be lesser, as all the negative charge has drifted and is now distributed between the two oxygen atoms. So if the negative charge density is lesser, it's not going to attract this H plus 1 ion. So this H plus 1 over here is going to be very less strongly attracted. So now more dissociation could happen. The dissociated ions would remain dissociated. They would not be attracted to each other because the negative charge density is lesser, and therefore the H plus 1 would be less strongly attracted. So less chances of them coming back together again to form ethanoic acid molecule again. So there would be more chances of dissociation. So what you're going to write as an explanation for this is going to be, so to explain this, so this over here is going to be your answer or explanation if it's being asked in your exam. Electronegative oxygen and C double bond O, this oxygen over here, has an electron withdrawing effect which makes our CO minus 1 ion stable, which basically means that it has lesser charge density and there would be less attraction for H plus 1 ions. So H plus 1 ions would not be very strongly attracted to it, so there would be more chances of dissociation happening. Now we are also going to discuss comparison between carboxylic acids, different carboxylic acids. So remember this, that electron donating groups, if they are attached to carboxylic groups, R, COH, this R, I'm specifically focusing on this R. So if they are electron donating groups, the acids are going to become weaker. And which groups are electron donating groups? So some examples are that you can have your alkyl chains or carbon chains, OH groups or NH2 groups, but they have their lone pairs, so they have an electron donating effect whenever they are attached to something. And also remember about carbon chains, these alkyl chains. Bigger alkyl chains are going to have more electron donating effect. So if you have two molecules, let's focus on two molecules. So over here I've drawn two examples. One is ethanoic acid dissociating, and you have butanoic acid dissociating. One thing that you're going to notice is that the difference between the two ions is that over here the carbon chain is much longer. If you have a bigger carbon chain, it's going to have more electron donating effect. And if there is more electron donating effect, electrons are being pushed by the carbon chains towards this oxygen. So the negative charge over here would increase in strength. There would be more concentrated negative charge because the carbon chain is pushing electrons towards this oxygen. And if the negative charge is concentrated, there is greater negative charge density, then this H plus 1 ion over here would be strongly attracted back to the oxygen and there would be less dissociation. So the H plus 1 would not be produced, the H plus 1 would be strongly attracted to this oxygen, and the reverse reaction would be favored, and the molecule is not going to dissociate that easily. So this is going to be a weaker acid. So if you have bigger alkyl chains attached to carboxylic groups, then the strength of the acid is going to decrease. And pretty much the same thing is going to happen with if an OH group was attached. So here's an example of another carboxylic acid which has dissociated. This was acetyl bond O and OH, and there's an OH attached on the other side. Remember, O has these lone pairs. These lone pairs are going to have an even greater electron donating effect. So the electrons are going to be pushed towards this highly electronegative oxygen. So instead of the electrons getting withdrawn towards the other groups, the negative charge over here is going to become even more concentrated, and this H plus 1 is going to be strongly attracted. So the basic idea is that the greater the more electron donating effect a group has, the more concentrated the negative charge, the weaker would be the acid. It's not going to dissociate. It's not going to produce H plus 1 ions. Instead, it would strongly attract those H plus 1 ions, even if it, for some reason, released or dissociated. The H plus 1 would be strongly attracted back again, and there's going to be less and less dissociation. Now, the exact opposite of this is going to be true, that if you have electron withdrawing groups, they're going to make your acids stronger. And the way they're going to do that, one of the most common electron withdrawing group is chlorine atoms. So chlorine they're highly electronegative, so they withdraw electrons, they pull electrons towards themselves. So the next thing we're going to discuss are carboxylic acids, but we're going to discuss chlorine substituted carboxylic acids, which where chlorine would be acting as withdrawing groups. So here you can see I have a chlorine substituted carboxylic acid which has dissociated. So this carboxylic acid group has already released the H plus 1 ion, and there's a chlorine group attached on the exact opposite side of the molecule. Now this chlorine has an electron withdrawing effect. It's going to try and pull the electrons towards itself. So if it does that, if it tries to pull the electrons towards itself, the electrons that were the negative charge that was concentrated over here on this oxygen atom is also going to be pulled towards this chlorine. So the negative charge density over here, it decreases. The negative charge density decreases, and the H plus 1 over here is not going to be strongly attracted to this oxygen. So there would be more dissociation happening because the H plus 1 is not getting attracted back again. The negative charge density is lesser because all the electrons, the negative charge, has been pulled by this chlorine over here. So the acid strength is going to be weak. It's going to be stronger. So more dissociation, the RCO minus group, this one over here, is going to have weaker attraction for H plus 1 ions. So there would be more dissociation. Now there would be variations of this molecule, chlorine substituted atoms or carboxylic acids. The greater the number of chlorine that are substituted over here, for example, if I have another molecule, so here I've drawn a molecule where there are two chlorines substituted. So if there are two chlorines substituted, the electron withdrawing effect would increase. And the negative charge that is concentrated over here would be even lesser. The negative charge density over here would decrease because now you have two chlorines that are pulling the electrons towards itself. So if the electrons get more distributed and they get pulled over here, the negative charge is going to be even lesser compared to the first case. And there would be even weaker attraction for H plus 1 ion. So what you can come up with is, so more Cl atoms over here in the carbon chain, there would be more electron withdrawing effect. The RCO minus 1 ion, this ion over here, would become stable because it has lesser negative charge density. So there would be weaker attraction for, there's going to be weaker attraction for H plus 1 ions. So weaker attraction for H plus 1 ions, so more dissociation would happen. Now another thing that is going to be an issue is whether that Cl is attached, which position the Cl is attached. If it's really far away from the negative charge, then the electron withdrawing effect is going to be there, but it's not going to be that strong because the Cl is very far away from this negative charge over here. But if the Cl atom is attached to a carbon atom that is very close to it, then the electron withdrawing effect is going to be stronger. In this case, in the second scenario, the electron withdrawing effect would be stronger because the Cl is right next to this negative charge over here. So this acid is going to be weaker. This acid is going to be stronger, relatively stronger. Reason being because the electrons are going to be withdrawn, the negative charge would be lesser, and the H plus 1 would have lesser attraction. So position of the Cl atom in the chain is also going to be an issue. So I've written down the explanation that if Cl atom or any electron withdrawing group is attached close to the carboxylic acid group, then there would be more electron withdrawing effect, and the RCO minus ion charge density decreases even more, making it even more stable, and there would be more dissociation. So between these two molecules, This Cl is close to the negative charge, so electron withdrawing effect is much greater. And so the negative charge over here is much lesser, and there would be even less attraction for H plus 1 ions. Now at the very end, we're going to summarize the reaction of carboxylic acids, uh, which are that carboxylic acids are considered to be as complete acids because they undergo all the reactions that acids undergo. They would react with metals, they would react with bases, hydroxides, and they would also react with weak bases, which are carbonates. So their reactions would occur with all three of them. Now I'm going to do the first reaction of sodium reacting, a metal reacting with carboxylic acid. Remember, it's the OHH that is going to be substituted in this reaction. So we are going to have RCOO and the H would be lost, and in its place, the H would be displaced by Na. And the H would go on to form H2 gas, but since only one H is getting substituted, it's going to be half H2 gas molecules. So for example, over here I have an actual ethanoic acid molecule reacting with sodium. It's going to produce the ethanoic acid, CH3COO minus 1. The H would be lost, Na would take its place, and half H2 gas molecules are going to be produced. The name of this molecule would be, remember this ion over here, I already told you this is the ethanoate ion. Ethanoic acid produces the ethanoate ion. So the name of this molecule would be sodium because it has sodium, and it would be called ethanoate. So this is what's going to happen when a metal reacts with carboxylic acid. Now the next reaction was a base, a metal hydroxide reacting with carboxylic acid. The reaction is going to be pretty much the same. This metal is going to come in and it's going to displace the OH, the H in the OH. This particular H would be lost. So the product that is going to be formed would be RCOO minus 1. The H is lost. Na is going to take its place. And a water molecule is going to be produced. That's the only difference because base or hydroxides plus acids, they produce salt and a water molecule. So let's try and do a reaction with a normal acid called methanoic acid reacting with it. NaOH, it's going to produce HCOO minus 1. H is gone, Na is going to take its place, and a water molecule is going to be produced. And this molecule over here would be called methanoic acid. So the ion that would be produced would be called methanoate ion. So the name of this molecule would be called sodium methanoate. Let's now do the third reaction of carbonates reacting with carboxylic acids. Pretty much the same thing. Sodium is going to come in, so it's going to be RCO minus 1. Na would take its place, the hydrogen would be displaced, and water and carbon dioxide are going to be produced in this reaction. What you just need to do is you need to balance this equation. So to balance this equation, there are two sodiums over here. So this should be multiplied by 2. 2 sodium salts would be produced. This would become 2 as well. And carbon dioxide would remain 1. So this is now your complete balanced equation. We can do this with an actual acid as well. Let's pick ethanoic acid, CH3CH2. This over here is propanoic acid actually. It's reacting with sodium carbonate. What it's going to produce is CH3CH2 COOH. The H would be lost. Na would take its place, and you're going to get water molecules and carbon dioxide molecules. They would be produced in the reaction. And we can balance this out. There are 2 sodiums, so there should be 2 molecules of this. So there should be 2 propanoic acid molecules. The name of this compound would be sodium propanoate. That is what this compound is going to be called. And also remember that carboxylic acids undergo all acid reactions. So another reaction that usually acids undergo is that they react with ammonia to produce ammonium salts. So we have an acid, let's pick any acid, ethanoic acid, CH3COOH, and I'm going to react it with NH3. What's going to happen is an ammonium salt is when the H in the acid is substituted by the ammonium ion. So this is what's going to happen in this particular case as well. It's going to be CH3CO minus 1, and the H over here has been substituted by the ammonium ion, which is going to be NH4 plus 1. So this salt is going to be produced, an ammonium salt. And the name of this molecule is going to be ammonium ethanoate. That is what this molecule is going to be called. Another very important thing that you should know is how to measure acid strength. What are the measurements that or the quantification of whether an acid is strong or it's weak? Now, one way is pH. You already know that what pH stands for. It measures the strength of an acid. The technical formula for pH is it's the negative log of H plus 1 concentration. So it measures, it's based on the concentration of H plus 1 ions. So you already know this that low pH, pH like 1 or 2, it means that the acid is strong. High pH means like pH 5 or 6 means that the acid is weak. But there's one problem. pH does not actually, it tells you the concentration of H plus ions. It does not tell you the acid strength actually. Because if you have a weak acid and the concentration is extremely high, then the H plus 1 concentration is also going to be very high as well. So remember this pH, it tells you about the concentration, not actually about the strength of the acid. The strength of the acid is actually how strongly it dissociates. The strength of the acid is, for example, if you have a molecule, let's call that HA, and it breaks down and ends up producing H plus 1 ions and A minus 1 ions. Now, if it's a very, very weak acid, now remember, the strength of the acid depends on the dissociation of the acid. So if it's a very, very weak acid, let's say there are 1000 molecules of this HA in a particular solution, and one of them only dissociates. So it dissociates very weakly. So 999 remain, one of them breaks down, produces one H plus 1 ion and one A minus 1 ion. So it's a very, very weak acid. And the concentration of H plus 1 is also going to be very low. So, but there's one issue. What if you added too much, if the concentration of the acid was very, very high? So let's do another example with the same acid. And instead of 999 molecules, I have a lot more molecules. For example, I have 10,000 molecules of HA in the solution. Now the concentration, I've increased the concentration. If I've increased the concentration of H plus 1 would automatically increase as well. So according to this ratio, if you had 1000 HA molecules, one of them broke down. So 10,000, 10 would dissociate. So 10 H plus 1 ions would be produced and 10 A minus 1 ions are going to be produced as well in this reaction. And what you're going to be left with would be according to the ratio, it's going to be 9, 9, 9, and 0. So if you had 1000 molecules, one of them was breaking down. If you have 10,000 molecules, 10 of them are going to be breaking down. But look at the H plus 1 concentration. The H plus 1 concentration has suddenly increased. So the pH value, it was the negative log of the concentration of H plus 1 would also be higher. And remember, we are dealing with the same acid. We're dealing with exactly the same acid. So pH is not a very good indicator of acid strength. It doesn't really measure acid strength. It actually measures the concentration of H plus 1 ions. So for the same acid, the concentration of H plus 1 ions can be higher. They can be lower as well, depending on what concentration you're using. So pH is not a measure of the strength of the acid. pH is a measure of how many H plus 1 constant ions there are present in a particular solution. You add more acid, you have more H plus 1 ions. You have less acid, you have lesser or fewer H plus 1 ions. Acid strength depends on how much it's going to dissociate. Acid strength is that if I take another molecule, and let's rub this off, and let's call that molecule HP. It's an acid as well, and it's dissociating and producing H plus 1 ions and B minus 1 ions. Now I add the same exact quantity of HB molecules 1000, and let's say it's a very, very strong acid. So 100 of them dissociate. So they're going to produce 100 H plus 1 ions and 100 B minus 1 ions. Now we're not really interested in B minus 1 ions. So out of 1000, if 100 are gone, you'll be left with 900. Now see what's happening. Now this is a fair comparison. You started off with the same exact quantity of the acids, 1000 molecules of HA and 1000 molecules of HB. But HB was a stronger acid. It was the stronger acid, so it ended up producing more H plus 1 ions in the solution. So now that's a fair comparison that this is a stronger acid because it's dissociating more. So remember, pH is not a very good measure. Instead, what is a good measure is the equilibrium constant, or Kc. For example, for this reaction, the Kc is known as Ka, or dissociation constant. It's products over reactants, H plus 1 concentration into A minus 1 concentration. These are my products divided by the ratio of the reactants, which is the acid. Because these two ions are going to have exactly the same concentration, this is written usually as H plus 1 squared divided by the acid concentration. Ha is your acid. Now this ratio, which is basically roughly products over reactants, you have more dissociation, the ratio would be higher. You have less dissociation, the ratio is going to be lesser. So if less products are formed, the reactants would be greater, the product would be lesser. K value would come out to be less. More products are formed, more dissociation happens. Like in the second case, there's more dissociation happening. So the products would be more, the reactants would be lesser, and the Ka value is going to be higher. So Ka actually measures the extent of the dissociation, not. So remember, when you're talking about the strength of an acid, or how quickly it dissociates, or how much it dissociates, you don't actually measure pH. pH is not a good criteria. It doesn't measure the strength of the acid. It only measures the H plus 1 concentration. It's actually Ka that measures the strength of the acid. So Ka. So remember, if Ka value is higher, it's a bigger value. That means more dissociation. That means it's going to be a stronger acid. Vice versa, a lot of times pK is used. pK is minus log of Ka. When you take the negative log, a higher value actually becomes a lower value. So remember this, if pK value is coming out to be lower, there's going to be more dissociation. The acid would be stronger. So K value higher, you get a stronger acid, and vice versa. If K value is coming out to be lower, it's going to be weaker dissociation. It's going to be a weaker acid. Or vice versa if pK value is higher. So remember this, that Ka is used to measure the strength of the acid, not the pH. pH is used to measure the quantity of H plus 1 ion in a particular solution. It doesn't really measure the strength of the acid.